The laboratory there. Yes. We're still waiting for Ivana. We're still waiting for one viewer. Ivana Wood, one of the reviewers. Is from Brazil. Yes, exactly. So. Hopefully, you didn't, miss times. I get yeah. It's 30. 30 for instance. Sorry, we are still waiting for one member, so that's why we're not starting. Maybe if not, I will read his recording instead. Okay, sure. He doesn't need to be present. Okay, thank you. He's here. He's here. Mr. Danilo. Artigas has translated two systems, Polish system, like Ph.D. at the University of French system, Paris at the here. My name is Martin Novak from the University, and I will share with you. Which include me. Welcome to the other members of the Professor Karim Nouri from the University of Paris. Professor Mariusz Dąbrowski, who is a referee, Professor F.D. another referee from University here. Professor Dąbrowski was from University of Szczeciński, and Dr. Ivan Agulo from Louisiana State University. Then we have the two members, Professor Mani Sakharariadou from King's College London, who unfortunately is absent, and Professor Szymon Pustelnik from Jagiellonian University. I also welcome two advisors, Professor Jakub Milczarek and Professor Zbigniew Grę. And of course, I welcome you all the audience here on YouTube. And last but not least, I welcome the most important person here. Thank you. Okay, so let us start. And somehow, traditionally, at least according to the Polish systems, I would like to ask Professor Milczarek to say a few nice things about the candidate.
Shall I speak here or use the microphone?
I think maybe I think everybody can hear you. It's yeah, you can just.
That's great privilege to be here for this day, which has come finally after 4 years. Let me start maybe with the fact that we met with Danilo in Marseille. That was in 2018, and Danilo was still a master's student there, and he got interested in certain subjects that I've been working that time, which was not very popular yet at that time, and related to the idea of bending a phase space of fields. Okay, so usually you have a field like a scalar field that you use in cosmology, and like in Platon field is considered to be flat, so the value of the field can go from -2 to +infinity. We started discussing the idea what will happen if we bend that space of the field. Then we wrote a first paper on that subject with corroborate, which discussed how it works when you apply that not only to the matter field, but also to the gravitational field itself. And then a sequence of papers appeared with Danilo on that subject on one side, on the Polish side, I would say. And on the French side, Danilo worked with Julien, with whom we know since like 2009, I think. Yeah. Going back to Grenoble time. And we joined forces to work together. And let me say that taking this fact into account, Danilo was really open-minded, okay? And this is one of his, I would say, characteristics. He's really open-minded person who don't scare to take challenges, to go to Poland for 2 years, okay, to Krakow. He liked to experience new environments. He liked to meet people, okay. So on one side, he is, very open-minded scientifically, but also as a person. I really appreciated, having Danilo in Krakow, in my team. He's really, he's nice guy, really. So that was really pleasure, and I'm really looking forward to collaborate with him. After his, next step in Japan, okay, that's gonna start later this month. Okay, so what can I say? I mean, I was very lucky to have such a PhD student, okay, and I wish you all the best
Thank
for
you.
your future career.
Thank you very much.
Thank you. Thank you so much.
Okay.
Now let me ask the candidate to present the main thesis of the week.
Yes. So let me start, and I will thank you properly after this presentation. Okay. As Professor Novak said, today I'm going to present you the topic of my PhD that I carried during those 4 years between Jagiellonian University and Paris-Saclay. That concerns the search of quantum features in cosmology, and that will more specifically talk you about the stochastic inflation and nonlinear field spaces. Let me first introduce a bit the topic. So, in 1927 and in 1929, Lemaitre and Hubble remarked that galaxies were going away from us, and that the further they were, the faster they would move. This is represented here in this diagram that represents the velocity of galaxies depending on their distance. And you can see that the relation is almost linear. They provided an explanation of this fact using the newly established theory of general relativity, namely that the universe is dynamical and expanding. This is represented here in this figure, where the universe is represented as a balloon, and you can see some small galaxies on top of it. And as the universe expands, as the balloon expands, you can see that galaxies go away from each other, although they are not moving in the universe. 100 years later, and after many observations, this is the current understanding of our universe that is called the standard model of cosmology. It would start from a Big Bang singularity where the universe is infinitely condensed and hot. After that, it follows a phase of inflation where the universe expands exponentially for a very short amount of time. It expands for a factor of about 10 to the power 26 in just 10 to the power minus 32 seconds. After that, the universe keeps expanding and cooling down, and as it cools down, the first atoms are created, and eventually the first light can freely pass across the universe, as represented here as a picture of this first light that is called the cosmic microwave background, CMB. The story continues while the universe keeps expanding and cooling down with the formation of the first stars and galaxies and so on. My PhD focuses on those first two eras, the Big Bang singularity and the inflation period, and I will refer to that as the primordial universe. On one hand, inflation has the good side of proposing naturally a mechanism that enhances quantum fluctuations to produce inhomogeneities, such as the one that we later observe in the CMB, seeding stars and galaxies. Therefore, represents playground for testing quantum field theory on curved background, and current observations support the existence of such an inflationary era. However, many models exist to characterize this inflation, and future observations will hopefully give us more hints about how to constrain those theoretical models. On the other side, on the other side, this Big Bang singularity represents the breakdown of general relativity. At that moment, we expect quantum effects to play a key role and to eventually modify the dynamics of the universe. So a current alternative to this Big Bang that I've just teased you is this Big Bang scenario. So imagine in the infinite early time a universe that collapses until reaching a maximal energy density, then bounces and expands as I have described before. The Big Bang has many pros. First, it regularizes the Big Bang singularity. Then it may actually be an alternative to the inflation era, but it also may provide the good initial conditions for having an inflation era. Therefore, the purpose of my PhD was to develop some tools to characterize quantum effects in the primordial universe. I will decompose this speech into two parts. First, I will introduce the nonlinear field space cosmology that provides us with a toy model of quantum cosmology that can give us some hints of the quantum features that one would observe and one would expect from a genuine theory of quantum gravity. On another part, I will introduce you the stochastic inflation that provides a formalism that aims to describe the backreaction of quantum fluctuations, those primordial inhomogeneities, on the cosmological background. Let me start with cosmology with nonlinear phase space. In physics, you can describe your system, your physical system, with a phase space. That is this graph, this diagram, QP. Q is called the configuration variable, and P is its canonical momentum. Here, for the example of a usual classical pendulum, Q characterizes, for example, the position of the mass, while P is proportional to the velocity of the mass. And all the dynamics can be obtained, can describe a curve on the phase space here in red. However, for some systems, it is not so obvious what plays the role of configuration variable and momentum. For example, in the case of a spin 1/2 in quantum mechanics, the states are described by a Bloch sphere where you have two states, a state 0 that describes, for example, the spin up, and a state 1 that describes the spin down. And here in this picture, it is not obvious what plays the role of configuration variable and momentum. If you go to the semi-classical limit of such a spin, all the states can be described on the surface of a sphere. This sphere is characterized by a vector S that describes the spin. And you can see that actually all those states can be described through canonical variables, Q and P, that are defined generally on the surface of this sphere. In other words, in this case, for a semi-classical spin, the phase space is spherical. And when you go to the limit where S, the spin, goes to infinity, it approximates the flat phase space limit. Let me drink a bit, sorry, already. And so this was the main idea behind the nonlinear field space theory that aims to generalize quantum field theory for the case where the phase space or field space is nonlinear and possibly curved. This idea has actually already been explored in the context of nonlinear quantum mechanics and in quantum gravity. And a few pros that I can give for the special case of a spherical phase space are that when you compactify both variables, the compactification may regularize singularities, such as the Big Bang singularity. And because of this correspondence between these canonical variables and spin variables, the quantization can be made easier by quantizing the analog spin system. We developed such a model, as Jakub described during my master's, for the case of the Sitter model, that is a universe in vacuum with a cosmological constant lambda. Here, the configuration variable describes the co-volume of the universe. A is the usual scale factor of the universe. And P is proportional to the Hubble factor, that is the expansion rate of the universe. So we proceeded as follows. We started from the usual Hamiltonian of the Sitter model, and we generalized the variables Q and P in terms of spin variables. We did this generalization by choosing the simplest possible choice in terms of spin variables, such that in the large spin limit, when S goes to infinity, one would recover the flat phase space case, so the classical de Sitter Hamiltonian. When you use this generalized Hamiltonian and analyze the dynamics out of it, you obtain the following evolution. This represents the evolution of the co-volume depending on time. And you see that the boundness of Q, of the canonical, of the configuration variable, introduces a phase of recollapse. So the universe expands and then reaches a maximal volume and collapses again. Whereas the boundness of the variable P modifies the Friedman equation for values of Q that are small. So here is a bit the kind of the shape of the Friedman equation you would have for small volumes. And you see that there is a correction, that is this term 1 minus rho lambda over rho c, rho lambda being the energy density of the cosmological constant, and rho c a critical energy density. So when rho lambda is equal to this critical energy density, the Hubble factor changes of sign, and you therefore change the Big Bang by a big bounce. To be exact here, because the cosmological constant is not diluted in the universe, we never really reach this big bounce, and it is sent to infinite early and infinite late times. But the idea is here. The next step was, of course, to quantize this model. And this can be achieved easily by quantizing the analog spin system. And when you analyze the dynamics of such a system, you can do it for low spin values, but it becomes a bit complicated for large spin values. Therefore, we had to proceed it as follows and use a perturbative expansion in orders of h bar, assuming that the spin is much bigger than h bar. This is a bit equivalent to replacing the operators by a leading order that is the expectation value of your spins, and a first order in h bar that corresponds to the correlation between your spins. We could see that after such an expansion, the phase of recollapse was preserved after quantization. So you can see it here in this graph that represents the evolution of Sz along time. And let me remind you that Sz is nothing else than the sine function of the co-volume. So here the universe expands and then collapses again. And for early and late times, this evolution, the evolution of the co-volume, is exponential, as expected from the classical de Sitter case. We're not able to conclude anything regarding very early and very late times because at that moment the perturbative expansion breaks down. This is represented here in this diagram that shows the evolution of delta Sz squared along time. And you can see that for very early and very late times, the order h bar becomes equal and even bigger than the leading order. Therefore, the whole perturbative expansion breaks down. Okay, but this toy model is quite simplistic. I considered a model in vacuum, and we know that our universe is not in vacuum. We have some matter components. So let me add some matter fields to it. And for simplicity, I will now consider that the phase space of gravity is flat, while I will curve the phase space of the matter components. So far, I've used the techniques of nonlinear field space theory for starting from canonical variables and writing them in terms of spin variables. But maybe we can use them to do the other way around, start from spin variables and rewrite them in terms of canonical variables, and maybe couple these canonical variables to gravity as we know how to do it. So that calls for the question, can we use these techniques to couple spin systems such as an Ising model to gravity? Of course, coupling spins to gravity has already been explored, for example, in the context of Einstein-Cartan theory or in more generally metric affine gauge theory. But here the methodology we adopted was a bit different. We started from a Hamiltonian of a continuous spin system, where S is aligned along the x-axis, and we re-expressed the spin in terms of field variables, a scalar field phi and a canonical momentum pi phi. After that, you can couple the scalar field to gravity using the usual covariant replacement here, where G mu represents the metric. And you can perform a Landon's transformation on phi, so that means change of variable, from a scalar field phi to another scalar field that I call psi. And you obtain the following action that is of the form of a Dirac-Born-Infeld action, dBi. To be exact, it's a dBi action if f is positive, and if f is negative, it differs because of this absolute value here. This was quite of a surprise for us, because the dBi action has been widely studied in the context of cosmology, as it naturally introduces inflation, for example. Therefore, we wanted to analyze the phenomenological consequences of such a model. And we obtained the following. So we found two solutions. This scalar field psi can mimic either some matter field with positive energy density that leads to an accelerated expansion that never ends. So in other words, an inflation that never ends. On the other side, it can mimic the presence of some matter with negative energy density, and that leads to a decelerated expansion. The case of negative energy density may sound scary, as it is very unconventional. However, it has already been discussed in the literature, for example, in the context of phantom matter, which happens to be a good candidate for dark energy and consistent with the supernovae data. In both cases, when you analyze the perturbations, those are tachyacoustic, meaning that they travel faster than light. That can also seem quite scary following our usual lectures in physics. However, the tachyacoustic perturbations were also introduced as a strong possibility as an alternative to inflation. They produce a nearly scale-invariant power spectrum, and contrary to what one would expect, they do not break causality. Still, this is not very, very nice regarding this spin model, because when I put an Ising model in space, I don't see an inflationary scenario or tachyacoustic perturbations out of it. So it may maybe represent a weakness of our study case. So let me go maybe a bit beyond. So far, I've considered only the case of spherical phase space. Can I do a study that is more general, step back a little, and have some study valid for different kinds of curvatures in the phase space? When you are curving the phase space, you are actually changing the symplectic form. This is the symplectic form of a flat phase space, and this is the symplectic form of a spherical phase space. And the symplectic form is what dictates the form of the Poisson brackets, or at the quantum level of commutators. We therefore considered a generalized uncertainty principle of this form with a correction of order beta p squared. This can be obtained from the spherical phase space in the limit where the spins are large. However, it can also be obtained with other geometries, for example, a cylindrical phase space. And it was introduced actually in the literature in a broader context, as in theories that present a minimal physical length, or in string theory as an example. Therefore, with such a generalized uncertainty principle, we started from the Hamiltonian of a single mode light, and we split the Hamiltonian as following, by just a change of variables, into a part that is a free Hamiltonian for new variables q and p that respect the usual commutation relation, and an interaction term of order beta. This interaction term will bring you modifications in the dynamics, and for example, modification in the dispersion relations for q and p. of order beta here. From this, you can infer the value of the squeezing amplitude of order beta. For the case of an n-particle state, the squeezing amplitude is oscillatory. This is represented here in this phase space. Usually, without squeezing, you would expect to have just a circle, like this blue circle. However, because of this oscillatory squeezing, the circle is squeezed into an ellipse that happens to turn into the phase space, reaching its maximal value here, and then decreases again. So the ellipse decreases again into the shape of a circle. For the case of a coherent state, you have similar oscillatory behavior for the squeezing. However, the minimum and maximal value of the squeezing grow linearly with time. This is represented here in this graph, showing the squeezing amplitude along time. In blue, I show the maximal squeezing amplitude, and in red, the minimal value. And therefore, it leads to a cumulative effect that can have big implications for observations. For example, if you consider photons of an energy of about 10 TeV and a travel distance of about 100 megaparsec, the maximal squeezing amplitude you can obtain is about 10 to the power 29. That's a huge effect that can actually already be observed through homodyne detectors, for example. Another case, if you consider two photons emitted at the same time of energy 1 TeV and 10 TeV, with a travel distance of 100 megaparsec, they would arrive at a different time with a time delay of about 7 seconds, which is, again, a big effect, big enough for being observed, hopefully. Let me summarize a bit this part. So, in one side, I consider the phase space of gravity to be flat, whereas I was curving the phase space of matter. And we showed that this could bring interesting phenomenology. For example, it can mimic the presence of exotic matter, such as phantom matter or tachyacoustic perturbations, and it can affect the photon dispersion relations, squeezing, or group velocity. Some of those effects, as I showed, are quite big, and maybe those are a way to constrain theories of quantum gravity. On the other side, I show that when you curve the phase space of gravity, this may lead to regularization of the Big Bang singularity and replace it, for example, with a big bounce. Big bounce scenarios have been widely studied in the literature, for example, in the context of loop quantum cosmology, in ekpyrotic models, in Einstein-Cartan cosmology, or matter bounce, and so on. However, in 1999, David Wans showed that for linear perturbations, some collapse and inflation scenarios lead to the same power spectrum. Therefore, the only way to distinguish those scenarios is through studying their nonlinear effects. An approach is, for example, to go beyond the linear perturbation theory and compute non-Gaussianities and so on. Here, I will focus on another approach, that is the stochastic inflection. After drinking a bit more. Okay, so before introducing the stochastic inflation, I will present you a bit more details regarding the production of inhomogeneities in the primordial universe. This is a pictorial view of the production of inhomogeneities, where I represent scales along time. And here, during the inflation period, the Hubble radius that represents the radius of the observable universe is constant. However, quantum fluctuations are expected to be stretched and amplified, and eventually they may exit the Hubble horizon. After inflation, the Hubble radius grows again, and eventually some of those quantum fluctuations may re-enter the horizon, but now representing inhomogeneities at large scales, explaining some of those inhomogeneities that we might see in the CMB. Now, this approach is valid for the inflation case, but it is also valid for a contraction phase. So the stochastic formalism that I will present is valid for both eras. And let me show how it proposes to capture some of those nonlinear effects. Here, let me represent you an observable universe in yellow that is homogeneous and isotropic. The deviation from this homogeneity and isotropy is represented with perturbations that can exist under a large variety of modes. You have modes with long wavelengths here and modes with short wavelengths. So in my idea, those quantum fluctuations that you start with. However, we saw that during inflation, all those modes are stretched and amplified. Those short wavelength modes are stretched and amplified, and eventually they may represent a large-scale contribution as well. So you should include them in your large-scale contribution and account for a continuous inflow of small perturbation towards the large scales. This is represented here in these equations, where in red I represent the evolution of the background and the long wavelength modes. And let me precise that those equations are nonlinear and taken in a specific gauge. And to render this continuous inflow of quantum fluctuations towards the large scales, I will add some stochastic noise to it, psi phi and psi pi phi. This noise is stochastic in order to render the randomness of the quantum behavior. However, this stochastic formalism relies on two main assumptions. First, the long wavelength modes are assumed to evolve as the background. That's why I have written the background and the long wavelength modes gathered in the same variable phi bar. I will come back to these points just after. Regarding the second assumption, here I described my quantum fluctuations classically. So I'm assuming that quantum fluctuations experience a quantum to classical transition. I will assume that this point is valid because it has been shown that in observables such as endpoint correlation functions, you can characterize this information only classically. So using classical formulation here is assumed to be valid. Let me focus, therefore, on the first assumption, namely that the long wavelength modes evolve as the background. For that, I will represent now a universe that is inhomogeneous and anisotropic, possibly. Here represented with a scalar field that depends on space. The question arises, can I represent such a picture with a set of universes that is each homogeneous and isotropic locally? And this is called the separate universe approach. And eventually, you would like to describe each of these patches with the stochastic formalism. So, for example, during inflation, but maybe even during contraction. My point was therefore to check the validity of such a scenario, and I focused only on the cases of scalar perturbations and for a background that is homogeneous and isotropic. We acted as follows. On one side, we started from cosmological perturbation theory, where we perturb the Hamiltonian and expand the Hamiltonian of general relativity. And we set the background to the case of a Friedman, Lemaitre, Robertson, Walker Hamiltonian. That is a homogeneous that is, a universe that is homogeneous and isotropic. On the other side, you start from readily a Hamiltonian that is homogeneous and isotropic, and you perturb it. That means that those perturbations are already homogeneous and isotropic themselves, leading therefore to the case I've described before with the stochastic formalism. This ensures indeed that perturbations evolve as the background. Now you can compare both approaches and ask under which conditions both approaches match at large scales. The separate universe approach is valid if, first, you can neglect gradient terms at large scales. So if k squared is much smaller than the pressure, the energy density, and the mass of my scalar field, where k represents the wave vector of my perturbations. These conditions can be obtained if k is much smaller than ah. So intuitively, that means that the wavelength of your modes is much larger than the Hubble patch, than the Hubble horizon. Another condition that is needed is that anisotropic perturbations and that the shift vector are negligible at large scales. However, all those conditions depend heavily on the gauge you choose. And that was therefore the main point of this study, the main difficulty of this study was to find gauges such that the separate universe approach represents a good approximation of CPT at large scales. CPT and separate universe have, let me reformulate. Separate universe can be understood as a truncation of CPT. It has less degrees of freedom, but it also has less constraints and less gauge degrees of freedom. Therefore, when you count carefully the number of degrees of freedom, you can compute that you have, for scalar perturbations, only one physical degree of freedom. That means two variables. So eventually, you could a priori find a gauge such that both approaches match at large scales. And that means that the physical degree of freedom should match at large scales. Here, I represent a few gauges. In the column CPT and separate universe, I indicate with a green tick whether all the gauge degrees of freedom are fixed. And with a red cross, I indicate whether some gauge degrees of freedom remain unfixed. In the last column, I indicate with matching whether separate universe gives you a good approximation of CPT at large scales or not. For the case of a spatially flat gauge, separate universe approach has all its degrees of freedom, gauge degrees of freedom fixed, and the same happens in CPT. However, when you analyze the matching of both frameworks, they match only in the case of slow roll inflation. Our purpose is to generalize the stochastic inflation beyond slow roll, for example, for a case of contraction. Therefore, we would like to find another gauge that is suitable for both approaches beyond the slow roll case. The synchronous gauge could appear as a good candidate as it fixes all the gauge degrees of freedom in separate universe. However, it leaves some gauge degrees of freedom in CPT unfixed. Therefore, you're not able to conclude anything regarding the matching at large scales of both approaches. We did find, however, a gauge that is suitable for this. The Newtonian gauge fixes all the gauge degrees of freedom both in CPT and in separate universe, and it matches at large scales. I mean, both approaches match at large scales in this gauge setting. The problem is that the stochastic formalism is not formalized in any of those gauge choices. It actually uses the uniform expansion gauge that happens to have gauge degrees of freedom unfixed in CPT. Therefore, it appeared to us as a necessity to provide with a clear methodology to fix the remaining gauge degrees of freedom in the case of CPT. And that was the purpose of this last article that just appeared on the archive on Monday. I have to correct a mistake I did in my manuscript. So using this methodology, we could not find any suitable prescription that fixes all the gauge degrees of freedom in CPT in the case of uniform expansion gauge. In my manuscript, I claimed that we have shown that there was no possible prescription to fix those gauge degrees of freedom. This is not really true. I realized that a bit later. There is still some hope for fixing the remaining gauge degrees of freedom. However, it is a very hard task mathematically, and we have excluded a large class of possibilities, including the one that is used in the context of the stochastic formalism. To finish with a good note, however, for the case of the synchronous gauge, we show that we could fix the remaining gauge degrees of freedom in CPT, leading to what I call a new synchronous gauge. We are left, therefore, with the analysis about the matching of separate universe and CPT in this gauge setting at large scales. And this leads me to my future directions and conclusions. I have shown that for generalizing the stochastic formalism, the question of gauges is a key question. And we analyzed a few cases and found one gauge such that the separate universe approach, that is an assumption of the stochastic formalism, gives a good approximation of CPT at large scales. However, it would be nice to find other such gauges where the separate universe approach gives you a good approximation of CPT. And this is something I am working on with Przemek Małkiewicz, investigating, for example, the case of this new synchronous gauge. Another approach could be to work with only gauge invariant variables. I showed that both separate universe and CPT lead to the same gauge invariant variables at large scales. And therefore, you could formalize possibly a stochastic formalism in terms of gauge invariant quantities. And that's another question that we are investigating with Przemek Małkiewicz. All this was done with the purpose of generalizing the stochastic formalism beyond slow roll. And I have established the domain of validity of the separate universe approach and of the stochastic formalism. Therefore, now we are left with applications beyond the slow roll case. This has already been engaged, for example, by collaborators in Portsmouth, in the case of an ultra slow roll inflation, or a stochastic collapse for a power law collapse, or again, for the case of uphill inflation. And we are now currently generalizing this study and trying to go beyond in collaboration with Emmanuel Frion, Taish Miranda, Vincent Venin, and David Wans. Finally, all the separate universe approach I have presented assumed those patches to be homogeneous and isotropic. However, it has been shown by collaborators in Japan that it is possible to construct a separate universe approach valid with anisotropic patches. This could allow to capture vector perturbations and tensor perturbations, and therefore the question arises whether we can formulate a stochastic formalism valid also for gravitational waves. And this is the point of my collaboration with Professor Tanaka and Yuko Hirakawa that I would like to conduct during my postdoc in Japan if I get my PhD today. Finally, to conclude, so I have first presented the possibility of having curvature in the phase space. I have analyzed the case of a spherical phase space for gravitational variables and showed that this could allow to regularize the Big Bang singularity. Also, the case of spherical phase space is interesting as you can describe the system in terms of spin variables, which may provide you with an easier way to quantize gravitational systems by quantizing the analog spin system. These provide us with a toy model that may give us some hints of the phenomenology you would expect from a theory of quantum gravity. On another side, I have considered the case of curvature in the phase space of matter and show that it could bring broad phenomenology such as mimicking exotic matter components, but also predictions about the squeezing of light modes and time delay of such quantities. To go further, it would be interesting to study the squeezing and time delay of other states, such as thermal states, using again a generalized uncertainty principle. And this generalized uncertainty principle could be even generalized a bit more into the so-called generalized extended uncertainty principle. Such predictions, could already be confronted with observations by, for example, the CTA collaboration, and would allow us to test some of those models of quantum gravity. On the second part, I have discussed the case of the stochastic formalism and the separate universe approach that approximates an inhomogeneous and anisotropic universe by patches that are locally homogeneous and isotropic. We did establish the domain of validity of the separate universe approach, and therefore of the stochastic formalism for scalar perturbations. The aim is eventually to go beyond and formalize the stochastic formalism beyond the slow roll inflation case. The stochastic formalism has interesting predictions because it allows you to compute, for example, the non-Gaussianity of the tail of the PDF that allows you to compute directly the abundance of black holes produced in the primordial universe. Another prediction that you could do if you generalize the stochastic formalism for the case of anisotropic patches is the computation of, for example, scalar-induced gravitational waves. All those predictions are hopefully are expected and will hopefully be observed by future missions, such as the NanoGrav and CaGra missions that are currently on run, or the DeSigo mission expected for 2030s, or I should mention, since I'm here, the Lightbird mission that is being developed by some of you. So to conclude, this work could allow us to use these observations to further constrain theoretical models about quantum gravity or quantum field theory on curved background in the future. And now let me thank you for having listened to me today.
Thank you very much.
Thank you.
So we move to the next step of the procedure, and we learn what the referee thinks about the thesis. Let me check if Dr. Ivan Danilo is here.
Yeah.
Oh, wonderful. So welcome. So usually what we do, we present now the reports. There is no necessity to present the reports in Excel. Basically, what the referees can do, they can concentrate only on some excerpts, more important parts, criticism, and of course the final conclusion. Okay? Mm-hmm. So maybe I will ask now in order of the protocol, Dr. Ivan Aglio, could you present your opinion on the thesis?
So this is not questions, right? This is just a summary of my opinion.
Yes, precisely.
Yes. Okay. I was not prepared for this, but let me. Maybe I should look for. Give me 1 second. I'm gonna just open the report I wrote. Yeah, it is. Right. As I wrote in my report, and I think it's available publicly and to all of you, I think this is a very nice thesis that investigates two different topics. One in perturbation theory in cosmology, as Danilo explains to us today, having to do with gauge issues in cosmology, which are quite a mess and technically difficult generally. And Danilo follows an approach based on Hamiltonian or canonical formulation, which I think is a very good strategy, because the Hamiltonian formalism generally provides a different viewpoint than the Lagrangian one, more geometric, and clarifies many issues which are quite confusing in the Lagrangian formulation. So I found that quite interesting. And in fact, I find the results quite clarifying in several points. I have some questions, in particular, because, you know, part of what is written in the thesis has now been updated, and my questions, my new questions come from that relation. But in general, I think the analysis is interesting, and it's going to be very useful for the community in general in comparing different approaches. So that part of the thesis is quite interesting. The second part, which was the second part in the manuscript, the first part in the presentation, has to do with beyond classical gravity, and trying to see, you know, if you know, trying to mimic quantum gravity effects by modifying the topology / geometry of the phase space. And I think that is also a quite interesting approach. And of course, that is a difficult problem in general, but Danilo follows a very concrete path, and, you know, under some approximations, of course, which I find useful and interesting. And he's able to unravel, you know, possible effects coming from quantum gravity, both in the expansion of the universe, and even more interesting in the way matter fields like radiation propagates across the universe, in the form of modified dispersion relations, squeezing, etc., which I find quite interesting. So I enjoyed reading the thesis, and I learned quite a lot from it. So globally, I think it's a nice work, and I think, you know, the quality of this work is beyond the threshold for a PhD. So I strongly support this thesis and his work. I have several questions I would like to ask for the, you know, in the session questions, but globally, I think this is a interesting, useful, and relevant piece of work.
Thank you very much. We'll come to this question soon after learning the opinions of the other two referees. So, Professor Danilo, may I ask you for your opinion and conclusions?
Hi, you hear me?
Yes, we do.
Okay. Yes, so that was a very nice, an excellent presentation. And as for the thesis, it was mostly, well, I did enjoy reading the thesis, but it was mostly a compilation of the articles of Danilo. But he managed to add a nice introductory material so that to make it all understandable, and present the relevance of the different works that he did. There's the whole work on cosmological perturbation and stochastic formalism that was very clean, mathematically rigorous, very impressive work. And then there was a series of different works which seemed connected from physical motivation, although not really, or like giving a complete picture. But that shows Danilo's broad understanding of cosmology and interest in all aspects of quantum gravitational physics. So these different works presented different, underlying different ideas, like the compact phase space for metrics, or modified photon propagations, linked with Born-Infeld and spin fields, which really, I found it impressive that a PhD student could work out all these different aspects in during those few years of PhD research. So overall, I really support awarding the PhD to Danilo.
Thank you. Thank you very much. And let me ask the last referee, Professor Mariusz Dąbrowski, for his opinion or excellent from his report, please.
Okay, thank you very much. I would not really follow the detailed description of my opinion. I could say that I had not enough time anyway to dig through all the details of the thesis because it was a challenge to look at it very carefully. But what I would appreciate is that really the candidate, in fact, looked at important matter of interface between quantum and classical and the relation or this quantum regime being present in the apparently classical era of the evolution of the universe, which is this early universe. So I think it's an issue which is very important for the whole field and not very much sometimes acknowledged by some of the people. In general, I was a bit confused at the beginning because of the length of the thesis, and I was impressed by the size of the papers included into the thesis. We have in Poland now the problem with such kind of theses which are hybrid, but I coped with the situation and was able to get the hints out of this presentation, and in particular I acknowledge today's presentation. I think it also gave me some kind of general insight into the topic and some kind of general background which was uniting all the components of this vast thesis. I would not perhaps enumerate all of the things, but of course I was impressed by many aspects of the papers, of the calculations. Obviously, the candidate is very well prepared to work in cosmology and also very skillful technically performing calculations. I made some comments which I will not read at this moment. I think the candidate can reply to them if I mean, it is formally needed by the Polish legal requirements. So anyway, I will not read all of them. The candidate knows and everybody could see them. I was very impressed by the the paper squeezing of light from the Planck scale physics and the observational effects which were presented during today's discussion about these delayed photons due to the generalized uncertainty principle influence and such kind of effects. So for my own sake, I made some kind of summary of the main outcomes, because in the thesis I felt I didn't find kind of a summary what was really important and what was really the breakthrough of these pieces of research. I mean, I was a bit I would say not satisfied, but curious why the papers were not so much kind of read by the community or cited by the community as kind of a result, despite the vast material being present in the papers. But I think it was due to the fact that simply the matter is large and kind of putting some order in the theory of particular approaches. So maybe people are still not yet even adopted or read carefully the results. So I would say that these outcomes, which I wrote in my last but one paragraph, is the use of the separate universes method for the feedback of the quantum perturbations. This is kind of a first outcome. The quantum description by means of the classical curved space, phase space. The third one, the indication that nonlinear quantum effects lead to squeezed quantum fluctuations. The fourth, the gap leads to squeezed states for photons with the observational results. And number five, the transition from spin space to the scalar field formalism, and further to DBI theory with negative energy density effects, etc., etc. It's a kind of a distributable. Maybe during the discussion I can also comment on that later. But anyway, overall, the results are very important and very impressive. Danilo is a hardworking, really scientist with future looking for the future development of many diverse problems. So this is a good base for being really a fantastic scientist. So I am impressed. I think that the thesis fulfills couple of 100% even the requirements for the PhD thesis legally, and I also would suggest its distinction as a kind of excellent work. So thank you very much.
Well, thank you very much. Now we are moving to the public discussion of the report. Let me remind you that everybody who is physically present or digitally present has a right to ask a question, but somehow traditionally we will start from our referees, maybe in the order in which they presented the results. So please, Professor Danilo.
Hey. First of all, Danilo, thank you for congratulations for the presentation. I think it was very clear. You talk in a very calm way, easy to follow and to understand. So congratulations for that and for the good, the amazing work that you have done. And also congratulations to the thesis advisors for guiding, a student to such an amazing and broad piece of results. I think you should be proud of yourselves. I mean, there are many people, several people in the committee, so I will try to focus on a few questions. And if there is time at the end, I can ask more if you want. But I want to focus on a few that I was a bit confused, or that you didn't explain enough in the manuscript. Let me start from the last part, the first part that you presented in the presentation, the last part of the thesis. The main idea that you use at the mathematical level is to use a compact phase space manifold rather than non-compact and standard phase space that we use for cosmology, for instance. But I was confused between the relation of compactness and curvature. Because to me, they are two different things, right? You can have a compact manifold, but manifolds do not come with a natural metric on it. And given a manifold, you can equip the manifold with many different metrics. However, when you were speaking, you were mixing compactness and curvature. And I was confused by that. So my question is there a metric on that manifold actually needed in your calculations? If it is needed, which metric do you use and why?
Yeah. So yeah, sorry if that was not clear. So indeed, you're right. There's a big difference between compactness and curvature, and so in this work that I've presented, at least the first part concerning curvature in the phase space of gravity and coupling spin to gravity, I considered a very specific case where the phase space is spherical. So it has constant curvature and both variables Q and P are compact. But you're totally right. It's actually not the most natural choice if you want to include curvature in the phase space, or just assume a broader class of geometries of the phase space. You could assume, for example, a toroidal phase space that is flat but has compact variables. This is actually what is done in most of those works in quantum gravity here by Aldo Riello, well, Etera Levin that is here also. Here I presented the case of a spherical phase space because it has this interesting property that you can describe the phase space in terms of a spin variable. That you cannot do it if you have, for example, a toroidal phase space. To answer to your question regarding the metric, when I'm in these works, we didn't formally used a metric of the phase space in the calculations, although it is assumed that it is here and that the curvature radius is given by the value of the spin. But actually your question is a question I had, and that led me to study more precisely the rigorous way of defining curvature in the phase space. And that's why in my thesis, I present this approach with Kähler manifold. That is, in my opinion, the most general, rigorous way of introducing curvature in the phase space. Yeah, this, I see it more as a toy model, which also has the pro of being more easy to manipulate and to do calculations with it and compute modified equations of motion and so on. I don't know if this answers to your question.
Yes, this answers to my question. Thank you. I just wanted to point out that the addition of a metric on this manifold is some extra structure that you are adding, and that should be clearly stated. So regarding also this topic, when you say that then you consider the quantization of a spin system as a proxy for the quantization of the gravitational degrees of freedom. I mean, my first question is, wait a minute, a spin system is fermionic. and the quantization of fermionic systems is completely different from. And I was expecting to read a clarification, and I couldn't find it. So I asked you, can you elaborate?
Yes, sorry. There's maybe a confusion. Yes, when I'm talking about spin system here, I'm not talking about a real quantum spinning particle. It's more a continuous it's more of a angular momentum that I quantize using just the algebra of a spin system, SU2 algebra. Those variables respect the Poisson brackets of a spin system, but to be rigorous, yes, when I talk about spin system, I should already work in quantum mechanics, and here all this approach is classical. Therefore, it should rather be treated as angular momentum variables. Yeah.
Okay. Also, now regarding the phenomenology, and because in this slide, right, because you do some mathematical hypothesis, try to include physics coming from quantum gravity or whatever more fundamental theory we are thinking about, and then you explore phenomenological consequences. And the natural question is to see if what you get is in fact what you expect from quantum gravity in physical terms. And I was surprised to see that the main corrections that you find is a recollapse when the universe is very big. Mm-hmm. And the surprise is because in a very big universe, curvature is very low, energy scales are very low, and quantum gravity is expected to arise at high curvatures and high energy. In contrast, we see here quantum gravity corrections, for low curvatures. Here the curvature is constant, sorry, but the volume of the universe is very big. So this is what you expect. Do you see any tension between this and what is expected from quantum gravity, or have you thought about it?
Yeah, let me think to give you a good answer, but okay, yeah, so I mean, I agree that even for me as well, it was a surprise, let's say, to have a phase of recollapse that is a quantum gravity effect that manifests at very large scales. But I mean, first, like, I would say, why not? And there are some works that do works in quantum gravity that do make predictions valid at large scales, predicting, for example, the existence of dark energy, dark matter, or effects of similar effects of photon delay are shown by Laurent Fredel, for example, in this approach. And having in thought his work, he shows that some quantum gravity effects could appear when, if I remember well, sorry, it was yeah, I'm thinking about the work of Laurent Fredel that is relative locality that you may be aware of, yes. Where assuming, I think it's they are interested in phenomena that could arise at large scales, where still G and H bar are non-zero.
I see. I see. So your viewpoint is that we should be open-minded.
Oh, sorry, that's just an example of work that exists, showing quantum gravity effects at large scales. But here I, let's say, followed this approach and showed what it could lead me to. Still, we can have some. I mean, I'm not saying when does this phase of recollapse happen. For example, maybe the value of Q max can tend to infinity, and actually, if you do so in this approach, you recover loop quantum cosmology. This model was constructed in a way that it exactly gives you loop quantum cosmology in a certain limit, and in this limit, this recollapse phase tends to infinity. So yeah, my let's say that my position here was more to be careful to accept the possible existence of such scenarios. I think about also the works of emergent gravity emerging from a more fundamental quantum structure. This is a bit how you can interpret this work as well, that the universe is the cosmological variables are described by a genuine quantum system, a spin system. Maybe the spin system is more fundamental than those gravitational variables. But to be honest, I try not to go too far in the interpretation of this model, because it is really a toy model. It has a lot of simplifications, a lot of assumptions that I can go into details if you're interested in. But yeah, I would say it is an example of quantum gravity effect that could arise at large scales. But okay. I would say I'm fully believing in it. Yeah, I don't.
Okay. So let me ask you a question about the other part, the cosmology part. I mean, I have some confusion now because I don't know which part of the manuscript you still defend and which part you have changed. Let me ask the question anyway, and you can tell me your opinion now. So according to your presentation, so can you go to slide number 26? So I can formulate the question more precisely. So my question is, what is the problem on having a gauge which is not complete gauge fixing, but it leaves some residual gauge freedom? In general, I would say, I mean, that is fine. And I mean, you are just partially gauging your theory. And as long as you compare gauge invariant predictions, you are good. Do you share that viewpoint? Because it was not clear from this slide.
I agree. As long as you go towards gauge invariant variables, eventually, a priori
predictions, I would say predictions, gauge invariant observables. Whatever you predict, if it is gauge invariant, you can compare two theories.
Yes. The subtlety here is that what we call gauge invariant quantities in separate universe are not gauge invariant with respect to CPT, because separate universe is a truncation of CPT. So if you look at, for example, the curvature perturbation, it has encoded some information regarding the anisotropic perturbations. And these are neglected, are really ignored in separate universe. So if you work in some gauge where these anisotropic degrees of freedom do not exist, for example, in Newtonian gauge, both gauge invariant variables match, there's no problem. The question is, under which gauge this quantity, the one of separate universe and the one of CPT, matches at large scales. And the big problem that arises when you consider a gauge which has unfixed unfixed gauge degrees of freedom in CPT is that when you will go to gauge invariant quantities, you are choosing a way to fix those remaining gauge degrees of freedom, right? However, it is not sure that this prescription will match the prescription that you have established in separate universe. This is why you have some gauges in separate universe. I didn't put those examples here, but you have some gauges in separate universe. Let me show the spatially flat gauge, for example. You have a gauge invariant observable that you can compute from CPT, and you can compute it from the separate universe perspective. However, they lead to different predictions beyond the slow roll inflation case. And this is the reason why, for the case of the spatially flat gauge, is that these observable gauge invariant quantities heavily depend on anisotropic degrees of freedom, and in particular the perturbed shift vector, which are variables that you do not capture in separate universe. Separate universe is really like another theory with less degrees of freedom, and you want to see in which domain it provides you a good and effective approximation of CPT.
Thank you, that was pretty clear. I have no more questions for now, so.
Thank you very much. So let us ask a second referee, Professor Li, for his tour of questions.
Yeah, so first I would like to congratulate you on your presentation too. It was an excellent presentation, very nicely illustrated, pedagogical, very nice explanation. Yeah. On the part on cosmological perturbation, it was a very nice presentation, very clear about the assumption, clean work, with an interesting outlook and plan for future research. It shows your, but you are a physicist, yeah. And as for the other part, it was a bit eclectic. Shows that you worked on several different things. In the thesis, it was a bit hard to see the common logical threads between these different topics. But in your presentation, you gave more importance to these works that you had just compiled at the end of your thesis. So it seemed more important than expected for me. And you nicely managed transitions between these different works, trying to show some common threads. So a bit some ideas about how to put these different ingredients together. So I will focus my questions on this section, so not too much on the cosmological perturbations. So about the first work on the compact phase space, it will be a bit similar to Ivan's question. Why did you consider a sphere? Is it just a mathematical trick? Or, I mean, why not a torus? Or, in fact, any other 2D compact geometry, like the 8 or any hyperbolic geometry? If you had used a torus, which is more usual with infrared and ultraviolet cutoff, basically, would you have got the same kind of phenomenology? Or do you see clearly the effect of having a positive curvature on your phase space? And what would you expect if you were to choose another compact surface with a negative curvature?
Yeah, that's a very nice question. Thank you. Let me think a bit. To answer the first part of your question, the main point of choosing a spherical phase space is because you can describe it with this spin, or rather angular momentum, that allows you to quantize it maybe more easily, and then to look for eigenvalues of look for the quantum state that solves the quantum Hamiltonian constraint and so on. But indeed, that's actually a main concern I had with those studies. It's one weak point, I would say, of this approach is that it has no a priori explanation of the fact that the phase space should be spherical and not another geometry. This is why I tried to develop a more rigorous way later after the publication of those works. That is the one with respect to Kähler manifolds. And actually, there is a theorem if you describe the phase space of two variables with Kähler manifolds. There is the uniformization theorem that tells you that you have only three geometries that are possible. The Riemannian sphere is the one that we basically make the analogy with here in this toy model. The flat case of like the torus, and a hyperbolic space with, I think, genus bigger than 2. But so maybe this could provide you a better motivation to choose for a geometry of the phase space. You have 3 possible cases, and here let's say we analyzed 1. Do I expect the same phenomenological consequences for a torus? I am not so sure. The reason why is that we analyzed the cylindrical limit of this phase space for the case where we compactify just the variable q, or we compactify just the variable p. In the case where you compactify just the variable p, so you have a q that is unbounded and p that is bounded, you recover loop quantum cosmology, and you have just the feature of the big bounce, although here it's in vacuum. And if you analyze the case of the other case where Q is compactified, you have just the phase of recollapse. And when you draw the equations of motion on the spherical phase space, I think I don't have them here, unfortunately. Yeah, sorry, I should have put the drawing. But yeah, when you do it, when you draw those trajectories, they represent okay. So here, if I have this spherical phase space, those trajectories are all parallel to this section, let's say. Imagine the section that curves the sphere in 2, and all the trajectories are parallel to this section. And this is for arbitrary ellipse here. I described the case of a sphere, but to be exact and to be able to compute the cylindrical limit, we introduced 2 radius on the sphere, like one that would determine the shape, the maximal value of Q, and another one for the maximal value of P. So actually, we're describing either a noblate or prolate shape. And whatever this, however you elongate this shape, all the trajectories are parallel to this section that I described here. So I imagine that if you go to the cylindrical limit and then glue together the two ends, you will still have the same equations of motion here. That means just a phase of recollapse, but without the big bounce, for example. So just to conclude, the phenomenology we had here with the spherical case, I think would not match the case of a toroidal phase space, and therefore I think that shows that indeed the curvature plays a role here.
Okay, a bit on more general grounds on this same model. It seems that you've been minimizing the importance of your model a little bit in the way you're presenting it. So I was wondering if you were seeing it as a toy model sans lendemain, kind of short-lived proposal, or if you really want to extend these ideas. I mean, how would you extend them to some non-isotropic cosmology or non-inhomogeneities? It seems like, from my point of view, that you're saying that we should look at the space of metrics itself and try to deform the geometry on the space of metrics. So kind of deforming the Wheeler-DeWitt metric, the supermetric, and maybe even change the topology of the phase space of general relativity. Is it in this direction you are proposing to go, or how do you see the future of this toy model?
Yeah. So I still find this toy model very interesting, even from a mathematical point of view, as a way to quantize systems. So, for example, if I take a system, I quantize it with those spin variables and go to the large spin limits. Here I show that the recollapse was preserved, but actually, if the spin goes to infinity, the recollapse potentially goes to infinity as well. So it's never reached. So for systems that are difficult to quantize, maybe this approach is useful, as it allows you to quantize your variables maybe more easily, and then find the kernel of your constraint. We could do that, for example, exactly in this model for low spin values, get the transition amplitude and so on. So I find that very interesting as a mathematical tool. To go beyond, I think that indeed a more rigorous prescription aims to possibly generalize the curvature, but one of my biggest concerns is how to generalize the Hamiltonian, because here, as I said, we chose a generalized Hamiltonian that was the easiest possible choice. But we have no further motivation for choosing this specific Hamiltonian. And that's a complication that often face models of polymerization and so on, but you need further motivations for knowing how to specifically generalize the Hamiltonian. So I actually prepared some proposals to go beyond this NFST approach. And you did some work similar with Jibril Ben-Achour, where you where you more rigorously introduce a way to generalize the Hamiltonian in loop quantum cosmology using symmetry arguments, for example, with the CVH, the algebra of CVH. And I think that was, for example, a tool you could use for to include in those toy models for knowing how to generalize this Hamiltonian. And then, as you mentioned, there's the possibility of changing the curvature, choosing other cases than a sphere. And for the case of general relativity, indeed, the configuration variable is the metric, the g mu nu, and the momentum is p mu nu. So that becomes now a very difficult task if you want to apply this method for the full case of general relativity. I think that this is maybe the direction where one should go to, but the calculations may be too hard to be carried out. So there's always, I think, some kind of balance between having a toy model and a really complete theory that is more fundamental. And another concern I have with this approach of nonlinear field space theory is the generalization of those coordinates that are defined globally on this manifold. If you use this more rigorous approach through Kähler manifolds, the phase space is defined only locally. And I am not sure whether this approach, such as the one we used in the toy model, is valid if you change, for example, the parametrization of your sphere. If, for example, I choose the center, the 0 point of Q and P, and I place it to in another point of the sphere, is this approach still valid or not? And I'm afraid it is not the case. So that's why I have some doubts here, and think that the best and the most rigorous approach is the one of Kähler manifolds. Yeah.
Okay. So I just have one other question. It's more on the generalized uncertainty principle and the propagations of photons. So you presented it as I modify the space of the phase space for geometry, and then I modify the phase space for the matter, and I try to see how, what happens, how it changes about the properties of the quantum photons, the squeezing, and all that. And there was a short discussion at the end of your paper, and I wanted to ask you to say a bit more on what are the possibilities for measurements of these effects due to the difference of different time scales, and how does it fit? How would it fit with the cosmological evolution and CMB measurements? And do you expect that if you were really trying to have a consistent overall picture, you should have a dependence of a generalized uncertainty principle parameter on the cosmological expansion? So the beta, should it depend on the cosmological evolution or not?
Sorry, I'm not sure I have understood the last point. Your last sentence.
Your generalized uncertainty principle, there's a parameter beta that drives the deformation. I'm just wondering if you think that it should be fixed in terms of just some Planck scale, or should it depend on the cosmological evolution and expansion?
Well, here in this study, we did consider beta fixed and small because we are doing a perturbative expansion in beta. It's true, it could be interesting and more general to assume, for example, a beta that depends on time. However, I expect, depending on how beta evolves, I expect the perturbative expansion to break down at some point. So one should be careful with that. And however, I don't know if you have a physical motivation for beta to vary depending on time. here we assume that the commutation relation was fixed with this correction.
Well, my question was a bit more general about the phenomenology of your proposal. What are the implications for the CMB measurements, and can we measure these effects from
okay, sorry.
cosmo measurements of astrophysics measurements?
Yes. Yes. So in this study, we had in mind, for example, gamma ray burst, long distance sources, and indeed the expansion of the universe could affect, for example, the time delay of those photons. We didn't consider this here. We did get this time delay just out of the modified commutation relation, but this should be an effect to take into account for a more rigorous prediction. And regarding the CMB light, I mean, yes, I think we could predict. I mean, those predictions should apply for the case of light photons arising from the CMB. I have doubts whether we can consider those sources with coherent states, or maybe one should consider thermal states. That's maybe the point of this future direction that I mentioned. But ideally, yes, I would be very interested in making such predictions for photons coming from the CMB. I don't know if this answers to your question.
Yeah, okay. Okay, sorry. Thanks. Well, that's all for me.
Thank you. Thank you very much. And let us move now to Professor Mariusz Dąbrowski. You have several questions included in your report. Please, it's your turn.
Maybe I will not ask all of them because some of them can be considered comments. But I would like to ask some kind of fundamental question from some piece of the relativity community, where when considered all these perturbations imposed on homogeneous and isotropic universes, I understand that what you call inhomogeneous universe is still a perturbative inhomogeneous universe. It's not one of these universes which are described as kind of a general solutions of Einstein's field equations, like Zekkere's solution or other solutions, Weinberg, Good, or many other solutions of this type. That your Friedman, Robertson, Walker universes, which form these separate universes or patches of homogeneous universes, are really kind of homogeneous in that sense. And you mentioned during your talk that in your future perspective, you see an extension of these separate universes being homogeneous and isotropic into an isotropy. So how you combine all these issues together? Because I mean, anisotropic, I mean Bianchi 1 or Bianchi 7 or whatever universe instead of this Friedman. So this is my first question to you. Okay, can you comment on all that and sort it out? Maybe I didn't understand everything carefully, properly.
Thank you for your question. Yes. So I think I see the point where that you're mentioning, which is actually in the context of the gradient expansion. that I didn't describe here in this talk. But to see it simply, the separate universe is the first order approximation in perturbation theory of the gradient expansion. The gradient expansion aims to be non-linear. The metric I have showed in the manuscript in the context of the gradient expansion is this, according to what I've read and the development made by Salopek and Bond, it is the simplest metric with vanishing shift and anisotropic degrees of freedom at large scales. You mentioned the case of the Chequeres model or the LTB model. I am personally not expert in those metrics, but I wonder whether the vanishing of the shift vector or the anisotropic degrees of freedom is really in the solution in this metric choice, or it is under a certain gauge fixing. Because here I would like to do the less possible gauge fixing, as you see, we need to do many gauge fixing assumptions later in the context of stochastic formalism. So I would like eventually, ideally, not to gauge fix the metric initially.
But your universe, this inhomogeneous universe, is not in the sense of a relativistic model based on some general metric. Simply, it's just a perturbative kind. I think so.
Okay. The one proposed the one proposed by Salopek and Bond is non-linear and should be a general solution. Let me check. Sorry. Mm-hmm. I think it is supposed to be an inhomogeneous metric that is solution of general relativity at large scales under the assumptions that you can neglect those gradient terms, shift, and yes.
Okay. So gradient terms are neglected. Okay, so it's kind of yes.
It's an expansion in gradient terms. Yes.
Reduced
definitely.
model.
Yeah.
Okay. So yeah, that maybe clears out. I mean, I'm since a group of relativists, including George Ellis, they always ask for considering the pure solutions of the Einstein's field equations rather than perturbative metrics. So that's the point here. So I understand that still it is kind of a reduced approach. Anyway, let me ask another one, which I wrote also in the paper in my review. Since you vary the physical fields within these patches of the Friedman universes, separate universes, you eventually these fields in principle could be understood that they could be related to some values of the fundamental constants, like gravitational constants in Brans-Dicke theory, for example. So is it possible? Have you considered such an opportunity?
Thank you. Yeah, that's, I think, so we did not consider this possibility, because here the idea is that at the beginning, patches are locally disconnected, causally disconnected. But later, after inflation, the Hubble patch grow again, and would eventually merge and lead to the observable universe. And this would eventually represent the inhomogeneities that we see, for example, in the CMB. So I did not start assuming that fundamental constants would vary from patch to patch. But
I understand that the physical fields are different in each patch.
Yes, yes,
Okay.
the perturbations, yes. The background is the same, but perturbations differ from patch to patch. And this is because those long wavelength modes will have more or less a constant value inside one patch, but far away in another patch, they would have a possibly a different value. So this was why the value of the fields depending on the patch you choose. But you could construct possibly a universe with some fundamental constant that vary from patch to patch, but that would mean that they are nearly constant on a patch, and that they are not, that they are slowly varying at large scales. I think that that's a possibility, and it could be used, yes, maybe in this context.
Okay, I understand now. Another one is about these negative energy density models. I'm kind of an old man. When you said during your presentation that phantom is a good candidate for dark energy, I could say that yes, now, but in 2002, 5, 7, people made a cutoff of phantom, even despite the observational evidence for this. People like Rocky Kolb or Turner were just cutting it. But now I don't really, I know the papers were theoretically, and you mentioned already this paper, which I also pointed out in my report by Nemirov. But I think Nemirov was considering this option for negative energy density as kind of a hypothetical opportunity. But could we really interpret physically what you have found here, that we have this negative energy density? Is it an interpretation, physical interpretation for that?
Yeah. So first, from more theoretical point of view, I would say the negative energy density is not a problem as far as the total contribution of matter has a total positive energy density in the universe. Here I've considered just one matter with possibly negative energy density, but maybe by adding some other matter components, this would not be a problem anymore. However, I mean, I am as concerned as you are, and I, to be honest, I didn't like at first sight to see this. and that's maybe actually why I try to do other studies adopting another point of view. And as I mentioned during my talk, these options of matter are not the one that I expect from putting a continuous sizing model in the universe, neither an inflation that never ends, neither a negative energy density. So for me, the easy conclusion that comes here is that this model is maybe too simplistic in some ways.
You somehow give up, but yeah, if I may, because I'm not, it's not, it's the defense, not a seminar, but if I may, I could tell you an interesting point related to these quantum gravity effects for the large scale. You know, you have the de Sitter model, and phantom is very close, but phantom is, even if you have W slightly smaller than -1, then there is a phantom. And then you have large universe and dense universe. So all these quantum effects are possible. Large universe, dense universe. And this is exactly what you have close to these, I mean, in these other ends for the de Sitter, where you have the bounds, this slide number, I think 11. That's kind of a comment here. Yes, okay. Yes, exactly. Because this is de Sitter, and de Sitter is close to phantom. Okay, so this de Sitter can feel this phantom peculiarity. But anyway, this is just a comment. Maybe I can shift to the last of my questions. Yeah, you said, I mean, this was discussed already at the very beginning about the big bounce. You had these plots where the big bounce is symmetric, and you mentioned these papers by David Wands about nonlinear perturbations being non-symmetric, etc. Could you possibly comment about this symmetric bounce? You know, because the universe evolves in time, and you have these bounces. You have them also in these ekpirotic or brane models, etc. How could you comment about the problem of keeping the second law of thermodynamics in that context of these symmetric bounces? I mean, because you have expansion, then contraction or whatever. So about these perturbations, how could you cope with these perturbations, with all these issues? Or you just disregard here this thermodynamical? Second law of thermodynamics. How could you say if everything is symmetric, then one could say that you can have time reversal? Yeah. Yeah, yes. Like this. Yeah, yeah.
On this picture, you mean?
This one, or in general, okay? Is it really symmetric, and how could you cope with the second law of thermodynamics in such universes?
I think it would actually never be. I'm not necessarily expecting it to be symmetric, because even if you consider a symmetric bounce at the level of the background, I'm not sure whether the evolution of quantum fluctuations would be symmetric during the collapse and the inflation scenario. So I think that anyway, as soon as you include quantum fluctuations, you would break this symmetry. I'm not seeing a problem here.
Okay, okay. Now, okay, I can now understand. Yeah. So, okay, it's enough. I mean, it's all from maybe maybe. Yes. Thank you very much.
Thank you very much.
Thank you. Thank you very much. So let us continue the discussion. Perhaps members of the jury, people from outside.
May I have just a comment, because I'm leaving shortly for playing. Okay, I'm playing in 2 hours, so I have to leave. So just I want to make a contribution to the discussion, to the points that were raised during that discussion before, especially the one by Ivan on the intuitive understanding of the recollapse, which is also related to what has been just discussed. Actually, this effect is always expected in case you have a finite dimensional phase space, which results in the finite dimensional Hilbert space. So it means that your number of degrees of freedom is finite, and you have always a certain inferred cutoff. Okay, so you have cutoff at the Planck scale, let's say, in the momentum, and then it has to be compensated by the inferred cutoff for the second conjugated variable, such that the product just gives you h bar, okay, times a given number. Okay, so this is always expected for compact phase spaces, not necessarily curved, but and also coming to that point by Ethera, when we pushed forward NSFT, non-linear field space theory, in 2016, the general idea was to bend a phase space of a field, whether that was a field of any matter or gravity. But eventually, one has to focus on a certain model, and the S2, the spherical phase space, was a kind of technically natural choice, given the fact that the U1 cross U1, which is a torus, was already studied. And the spherical phase space, importantly, is non-product. Okay, so it's not a cotangent bangle, which also leads to certain new features that we wanted to understand. And of course, the fact that this is related with angular momentum gives very handy way to treat the modulus. This is what Danilo have shown. And concerning the curvature, I mentioned curvature is not necessary to actually generate those effects, but the curvature is always there. We have the so-called symplectic tripole, which tells us that if we have a symplectic manifold, not necessarily cotangent bangle, we have almost a complex form definement that we can always define a metric, okay, in a unique way. And for sphere, in particular, this can be done. It has been studied in other paper of us, and we explicitly derived the metric and the associated curvature. Okay, so this is very compatible. Usually when we deal with the compact, when we deal with phase space, we don't discuss curvature, but this can be mathematically well defined because of the compatible tripole. Okay, so that's my contribution to the discussion.
So this was a comment. So.
That was a comment. Sorry for that, but that was a comment. I don't have any questions. I understand everything, and I'm very happy with that.
So, you follow our digital audience. Do you have a question?
But we first have to ask the other members of the committee who are online to ask questions and to make comments.
We have when we look at other members here,
you can start
as well online. I see Professor Shimon Puster.
Thank you, Jakub.
Okay.
Do you have a question?
Yes, I do have. Maybe. First of all, I have to say that I'm an experimentalist myself, so I'm not trained in theoretical physics, neither in field theory or quantum gravity. So I apologize in advance if my questions are not adequate, but I want to make two comments. well, a comment and a question. So first a comment. If I understand correctly, somewhere during your presentation, you said that the light that will approach from the distant object because of the models will be squeezed very strongly. I remember 10 to 29, which is a number I cannot even think of. But I gotta say that I believe, I cannot prove it right now, but I have a very gut feeling right now that this sort of squeezing, even numbers, even orders of magnitude smaller, would have a dramatic consequences. So I particularly, something like that would be true. The light reaching us from, for example, this radio burst that you were talking about, or some FFPs would be squeezed in close to this, or maybe I don't know, maybe even smaller, would be dramatic, right? Because what we have right now in optical domain is roughly 30% squeezing, 20% squeezing of light. So this would be a dramatic change, and I cannot name it right now, but I would say that this is probably an idea that could be cross-referenced with the existing data and verified if the model is correct or not. I mean, so that's my comment.
Actually, if I can bounce on that, there some. I mean, I'm not directly in talking with these people, but a collaborator with whom we wrote this paper, Kylian Martineau, is in close contact with people of the CTA collaboration, and they would be interested in exactly cross-correlating this possibility. Yeah, and I have a same fear with you, because for such a large value of the squeezing amplitudes, this means that we have actually a large value of these X and Y parameters, and actually this may lead to the break of the perturbative expansion that we used. Because of these corrections here that are assumed to be small compared to h bar over 2. But even if this exact value of the maximal squeezing is not correct, the most interesting fact here is the cumulative effect that would be correct at least for some time before breaking this perturbative expansion, and that could lead still for some observable effects.
Yeah, so as you said, probably you can already look into or somebody else could look into the data and try to see if anything like this is present, although that might not be so easy to detect squeezing from the light coming from astronomical sources. Okay, but I want to ask you about something that bothers me a little bit. I have friends in Poland, or semi-Polish, who work on this tachyonic quantum gravity, where, you know, when they talk, there is the whole different realm of particles that are moving with superluminal velocities. And what I learned from them, and this is maybe the only thing that I learned from what they are telling me, is that these two realms are separate from one another, right? One existing below C, and then the other one exists above C, and everything is fine. But the problem is that the communication between these two realms, you cannot cross C either from low to high and high to low. But then somewhere in your, I mean, so can you comment on this? Because you mentioned at some point that you have this super fast propagating signals, and I assume there is some sort of a communication between them and the real world, right? Can you comment on this one?
Yeah, thank you. That's a very good comment. So I think the way tachyacoustic perturbations are introduced as an alternative to inflation is because inflation, I mean, the regular cosmology without taking into account inflation faces a problem that is the horizon problem. That is that we see in the CMB points that are that have more or less the same temperature with just a very small difference that without inflation wouldn't have never been causally connected. However, if you have tachyacoustic perturbations, so perturbations that travel faster than than the velocity of light, they could have connected those different points, and that's why it is presented as an alternative to inflation, solving this horizon problem.
Okay, but then the problem of communication between slow and fast universe would come around. I mean, I'm not sure to which extent this is a fundamental problem, but somehow the tachyons ought to interact with regular particles, right?
Yes, with other matter components, I don't know. I'm maybe not so sure.
Well, but if you see them in CMB, right? If you see them in CMB, it means that you can detect radiation coming from them, right?
But, yeah. But they could have an impact more on the gravitational expansion, maybe on the space-time itself.
That's fine. You know, it was just, I understand that it may be a little bit beyond. So I was curious. That's why I asked my question. But overall, very nice work. Thank you very much for the presentation. And that's it from me.
Thank you very much.
Thank you very much. Doesn't have one member? Yeah. Yes, which is officer of YML, which is.
Yes. Okay.
Yes. So, yes, please go ahead.
Thank you, Danilo. It was a great talk and also a very interesting manuscript, a huge amount of work, and you explained it very, very well. So I'm very happy, of course, with your work and with your talk. You had a lot of very smart technical questions. So I'm going to make it very brief and very short with only one question, which is actually not at all related with your work. But the title of your thesis is Quantum Features in Cosmology. So my question is somehow philosophical. Are there any deep reasons why you think cosmology should be considered as a special, as a specific, as a particular quantum system, different from the others? Of course, I have in mind interpretational issues like many words or relational quantum mechanics, and also, of course, the transition from quantum to classical that you have mentioned in your talk, and which is obviously a specific question in the framework of cosmology. So could you make a kind of general comment on this? I mean, beyond your work.
So on why the primordial universe should exhibit quantum features, that is.
I mean, yes, maybe I can summarize the question like this. Is the universe a special quantum system? I mean, are you sure that we can describe the universe with a wave function exactly as we describe an atom with a wave function? And how do you treat the Copenhagen interpretation for the universe? I'm sure there is no simple answer to that. I would just like to know if you have some thoughts about your personal view about this very well-known and very complicated problem.
Well, I would say, okay, I would adopt an approach that is maybe simple, but it is in terms of effective field theories. And as far as I go back in time, the universe becomes more and more dense, and at some point we do expect quantum features to appear first as a theory that could resemble something like quantum field theory on a classical curved background. But then if you go closer to the singularity, I would expect really quantum effects even at the level of the background, the gravitational background itself. And for me, the biggest motivation of this is that we know that general relativity breaks down, that general relativity is itself an effective field theory, an effective theory of a broader genuine theory. But I mean, I can always push this question a bit more if I want to answer a bit philosophically to your question. Are we ever sure that we will find a theory that describes everything, and that even if we did find a theory of quantum gravity that explains the Big Bang, we could go, I mean, even beyond. So yeah, that's a very philosophical question to which I don't have the answer.
Okay, my question was not so deep, actually. It was not even related with quantum gravity. It was mostly related to the quantum to classical transition when you have no exterior system. You have no classical system with which to interact. So as your thesis is called Quantum Features in Cosmology, to me, this is the first naive question. But I think you must be very tired, so I don't want to insist, and I'm very happy with everything you have said.
Thank you. Thank you.
Sorry.
I will. We just connect for the deliberation. Yes. Okay. Yes. And we. So I mean, this concludes.
Yeah. Unless you want, I would just want to add maybe one word.
Yes, please.
So Danilo, thank you very much for the presentation. I agree with all of the members that you did a very nice and very pedagogical presentation of your work.
Thank you.
And then you managed, to put everything in a consistent way, all the parts of your thesis, even though the different parts are quite technically disconnected. And it is nice that you have a global physical view, and you manage to use different techniques to present, to, at the end of the day, have a very nice and complete thesis. So this is very, very interesting. But I may have two questions, maybe. So many of the questions I wanted to ask, I have, in fact, a bunch of questions, but let me just give a few of them. One of the questions concerns, let me see, yeah. You see, when you talk about in slide 8, the dynamics of the spin, you start with, see the motivation for saying that we want to deform the phase space into a curved phase space. But you know that there exist some Lagrangians and some Hamiltonians to describe the spinning particles.
Yes.
And so my question is, why don't you start with this kind of action that will provide you with the phase space for the spins? Because I think, if I understood right, you said that there is no phase space for the spin. We don't know what is P, what is Q for a spin particle, but in fact there exists some things like this in the literature. So I don't know. So my question is, are you aware of these descriptions? And yeah,
for a spinning particle with mass and charge, or you are describing?
Yeah, like a representation of the Poincaré algebra somehow, really with the mass and the spin, and you can describe the full dynamics of such a representation.
No, I'm not aware of this work. And here, yeah, the approach we used in those models is a bit different, because it's not really a spinning particle, since it doesn't have mass and charge.
But you end up with something which looks quite similar. I mean, of course, it is different, but there are some similarities. And of course, I had the same question concerning the ambiguities, or considering these ambiguities on the geometry, on the topology, and also why, yeah, you can imagine having something which is not even a geometry. Maybe you see, instead of having a cosine p, you can have a cosine 2 times p, and in that situation, you still have something different.
Yeah.
And have you thought about all these ambiguities?
Yeah. Yes, that was one of my major concerns, is that I didn't have any further motivation to explain that this was the correct generalized Hamiltonian and not another form. That's why I mentioned earlier when answering to Etera Levin that we could use symmetry arguments, for example, to generalize the Hamiltonian such that this symmetry is preserved. So, well, the CVH algebra, for example. For me, that's the easiest solution I find so far for having a motivation that constrains the form of the generalized Hamiltonian. I would have liked to explore this case, but I didn't have time to.
Okay, so maybe one last quick question, and you can give a very quick answer to this question. So concerning the separate universe approach, the second part of your presentation, the first of the thesis. So there seems to be, I mean, you have already discussed this aspect with Ivan. So what is the problem? The problem is the SU approach, or it is the gauge fixing process? See what I mean? Because it seems that
the SU approach has been shown to be valid, to be a valid approximation of CPT, but it has been shown to be valid, but not in which domain it is valid. And that was our work. It was to establish this domain of validity. And it is valid if you can neglect gradient terms, if you can neglect anisotropic terms, but all those conditions are gauge dependent, actually. Even though in some work you can say that you have a.
But I just but it's okay. But I just wanted to know that indeed the problem is the SU approach. It is limited. It has a domain of validity.
Yes,
and that's
definitely. Yes,
same process. It is very well. It is completely under control.
Yes. Yeah.
That's the only.
Yes.
So I'm happy with that. And again, congratulations for presentation and for the answer.
Thank you very much.
I'm done. Thank you.
Since I'm the last member of the jury, so let me only mention that I had a question, but it was asked by Professor Dobrowski, and you answered.
Okay.
So I do not have more. I do not see the question from the audience. I think so. I think we can close that part of the meeting, and the next part will be intentional. We'll be discussing that voting, and then we'll come back to announce the results. Thank you.
So, do we stay at this here, or?
Yes.
Best friend. I'm just taking
So please just
Excuse me, we cannot hear anything. Look, people in the...
It's in French.
Can you hear?
Okay.
I'm
Now
sorry.
yes, now yes.
Ah, yes. Okay. Anyway, it was in French. So, well,
Pas de problème.
okay, I don't know any words in Polish, but I should say no problem as well. Okay. Ouais, donc toute une félicitation et puis on te souhaite vraiment bon vent pour la suite au Japon. Voilà, bravo.
Merci.
Donc, Julien,
Ouais, donc,
tu peux dire le mot, so
yeah, cool.
so
It will be in French too. It's always easier for this kind of words in the native language. Donc, Yacoub a fait l'entrée en matière, je sais pas, l'amuse-bouche, faire le café Calva, a priori, à Starfix, enfin, ce qui est prévu, j'imagine. Juste pour dire que Danilo, on le connaît depuis longtemps à l'IS. Il a commencé avec un stage en L3 ici, qui était sur l'inflation et la LQC à l'époque. Et puis ensuite, on a beaucoup souligné son ouverture d'esprit. Il est allé faire un an à Padova, puis un an à Marseille, et puis il est revenu vers moi pour construire cette thèse en co-tutelle, donc entre l'université Jagellonian à Cracovie et ici. Et donc, Danilo, il a passé un an à Cracovie, puis 2 ans à Orsay, puis un an de nouveau à Cracovie. Donc, ça a été un plaisir de l'avoir pendant les 2 ans ici. On a fait moins de papier qu'avec Yacoub, c'était pas du tout une compétition. Mais c'est vrai que il a eu la chance d'avoir peut-être un peu deux manières assez différentes. Comment dire, quelqu'un parler de moi qui aime bien des longs papiers, des gros papiers, probablement qui aurait pu sortir plus tôt, mais voilà, c'est une manière de travailler comme ça. On aime bien prendre son temps, comme Karim l'a dit, et faire plutôt des publications plus rares, mais prenant plus le temps de les faire et d'explorer toutes les pistes. Donc, tout ça pour dire qu'effectivement, Danilo, il a fait un peu le grand écart. Ça se voit pas tant que ça, parce que il a travaillé énormément sa préparation pour mettre les choses ensemble, pour se construire une idée globale de ce qu'il avait fait. Et c'est pas fin. Cette cohérence qu'il a montrée, elle est pas fausse, elle est pas fake. Mais et c'est parce qu'il a beaucoup réfléchi dessus. Mais effectivement, il y a eu beaucoup de grands écarts entre des questions de presque de pure relativité générale dans le régime perturbatif, ce qu'on a fait, bon, la partie inflation stochastique, et puis des questions beaucoup plus spéculatives sur des tentatives de faire de la gravité quantique. Et je pense, peu de thèses qui sont comme ça, où on couvre beaucoup d'aspects, et c'est sûrement pas toujours des thèses simples à mener, parce qu'effectivement, il faut s'approprier tout un tas d'outils qui ne sont pas des moindres à s'approprier. Et Danilo a su faire tout ça, en particulier. Il y a des belles annexes dans les papiers où, en fait, faut pas croire, mais ces annexes, c'est peut-être des dizaines de pages de calcul avant d'arriver au bout. Et Danilo, il a su faire ça pendant les 2 ans où on a travaillé ensemble, et 2 ans pour moi, on va dire aussi. Donc, c'était vraiment un plaisir de l'avoir, et je suis très heureux qu'il ait eu cette bourse pour le Japon. J'ai peut-être tort, mais j'ai l'impression que ça correspond bien à son tempérament, pas spécialement le Japon, mais de se dire, tiens, on va aller continuer des univers séparés à 12 heures de vol d'ici, et dans une culture très différente, mais c'est peut-être ça aussi, un tempérament qui te colle, regarder plein de choses différentes, c'est peut-être aussi ta manière de faire de la science, et c'était assez agréable de faire ça avec toi, de découvrir plein de choses en fait sur ces approches aussi. Moi, j'ai découvert, j'ai appris plein de choses.
Je suis heureux aussi de tous les compliments que tu as reçus aujourd'hui, qui sont grandement mérités. Et j'espère qu'on se reverra. J'espère que ce sera au Japon. On se reverra. Voilà.
Merci.
Maintenant, la place est encore à toi.
Merci. C'est encore à toi, mais tu sais, so we have
Voilà.
more things to do. Again, in French or in English, that too, maybe you can say English is okay. English is okay. So,
yeah, right. Yeah.
Okay. The sermon des docteurs.
I would also like to
Sermon.
thank people. So maybe I can.
It's up to you. I mean, you can pronounce it later. It's a choice. You can pronounce it or not, as you wish. So you can say a few words, and then when we drink something, then you pronounce it in front of everyone. That's okay as well. Okay, vas-y.
Okay. Yeah, just since we're in the emotional part, let me thank people as well. And well, I would like to first thank Jakub that he's not here, but that I know he's thinking about me right now. And
Depends on the order.
But I had a very nice time with Jakub in Poland. And I felt very welcome in Poland, and I really enjoyed my life there. And I am very thankful to him for not treating me as a student, but treating me as a researcher, an independent researcher, and always supporting me in my choices of research, but also of research trips and so on, and projects. So I am deeply thankful to him for that. I'd like to thank also, of course, Julien. So maybe let me switch to French. Ça a été aussi un honneur pour moi de t'avoir d'abord comme superviseur de stage et puis ensuite comme superviseur de thèse. Je me rappelle que ça s'est joué à rien. J'ai toqué, j'avais envoyé des mails et sans réponse. Finalement, j'ai toqué au bureau de Julien et il se trouve qu'il y avait eu une panne de messagerie. Et si j'étais pas passé, en fait, on ne serait pas connu, on n'aurait pas commencé tout cela ensemble. Et je voulais te remercier pour énormément de choses. D'une part, te remercier scientifiquement pour tout ce que tu m'as apporté, tout ce que j'ai appris en ta compagnie. J'aimerais te remercier d'un point de vue plus personnellement, parce que malgré ces problèmes administratifs, s'il y a un bruit stochastique administratif constant, c'est toujours placé comme un attracteur du background pour me guider et me mener à bien vers la thèse. Et finalement aussi, j'aimerais te remercier humainement parce que je trouve que tu es une super chouette personne au-delà du côté scientifique. Et j'aimerais vraiment qu'on reste contact possiblement au Japon.
Oui. Si tu repasses ici, ce sera le bienvenu.
Voilà. Donc, merci pour tout, Julien. Et j'aimerais remercier Vincent Venin, je ne sais pas s'il me regarde son nom, mais que je considère comme mon troisième directeur de thèse, pour qui j'ai une grande admiration aussi, qui m'a appris énormément scientifiquement et qui m'a réellement encadré aussi et formé et appuyé dans mes projets. Et donc, Vincent, si tu me vois, je te remercie et ce sera avec plaisir que je collaborera à nouveau ensemble ou échangera. Voilà. I would like to thank all the members of my jury, of course, and my reviewers for reading this. I know very long thesis. And thanking you for all your nice comments today. That's very, very nice to hear. More generally, I would like to thank all my colleagues scientifically that made me grow up as a researcher, and in particular researchers that received me very well in their institute during some research trips. I know some of them, or maybe also looking at me right now, so thank you. And I would like to thank my friends and colleagues, both in Poland and here in France, or even in other parts of the world. But you highly contributed to the fact that I enjoyed this thesis and just the life beside the thesis. And I felt very well here, even though I was like not in a Polish institute, not in a French institute. I was like always half, just half here, half there. I really felt welcome in both places, and as if I was, a real member of the teams, and so thank you for that. And maybe I would like to say a few words to my family also, which I know couldn't come, but is watching me online, and I will maybe switch to Spanish, but quería decirle muchas gracias por todo, porque, bueno, ya saben, es mucho, o sea, hay mucho que agradecer, y gracias por apoyarme siempre, gracias por estar. Y nada, para que sepan que el amor que tengo por ustedes es algo mucho más difícil de explicar que la evolución del universo, cosas así. Y por todo, muchas gracias. And I can read the Polish.
On t'applaudir ensemble.
Ah, c'est ça.
Attends, après, on va juste après. On passe le moment avec nous.
Okay, so in the presence of my peers, having completed my doctorate in physics and having thus practiced in my quest for knowledge the exercise of demanding scientific research by cultivating intellectual rigor, ethical reflexivity, and respect for the principles of scientific integrity, I commit myself for what will depend on me in the continuation of my professional career, wherever the sector of the field of activity, to maintain an honest conduct in my relationship to knowledge, my methods, and my results. So I invite you, all of you, to go outside and maybe enjoy some food and drinks. Sorry for those who are online, but
enjoy
yeah.
it. Congratulations, and thank you very much.
Thank you very much.
Thanks you all for the part of the it's very.
Thank you very much for your participation. Thank you. We are closing the meeting.
Thank you.
Bye.
Felicidades. A celebrar.
Muchas gracias.
Congratulations.
Ivan,
Bye.
Un abrazo. Chao.
a nice day for you, and it will be a nice evening for the one in Europe.
Yeah.
Thank you, Julian. Bye-bye.
Ciao, Etera.
Ciao.